Hey, good morning, everyone. Today you're going to finish off the topic of static electricity with what is probably the most awe-inspiring and dramatic version of static electricity, which is electrical discharge and lightning bolts. You more commonly know this just as a spark. And we've all experienced this under one condition or another. Maybe by accident, you've been taking off your coat in the middle of winter when you get home and you go in, you touch the light switch and you get a spark. Or you'll notice that when you're in a house with sort of thick, shaggy carpet and you rub your feet across the carpet and then go touch your sibling, you give them a shock. So this shock is an application of static electricity. So what happens, and we've got a nice little simulation here for you to try out, cleverly nicknamed John Travoltage. You'll have to click on the link. It's not going to work within the OneNote lesson. So you click on the link, it takes you to one of these PhET simulations. And there's two parts of this simulation you can click and move. First is his foot across carpet, and the second is his finger. Okay, so we know and we learned previously that when you rub two objects together, you end up with charging by friction. So when you rub your feet across carpet, especially sort of thick, shaggy carpet, we have friction taking place. And so we see that your body rips electrons off the carpet, and you as a person actually end up with a negative charge. Now, even though you end up with a negative charge, we do know as well that those negative charges repel each other. They don't actually want to be on you. So the act of rubbing your foot, again, causes you to build up negative charge. But if there is a way for them to leave your body, they will. And so that's where touching a conductor comes into play. Your finger essentially represents a pathway for these electrons to get away from you. Now, they can't just easily leave your body because the surrounding air is a good insulator. But as you bring your finger close to a conductor, charging by induction happens. You learn that as well. Basically, you're going to end up making that door handle temporarily positive by bringing your finger close to it, which unfortunately they don't show in the simulation. But suddenly those electrons are extremely attracted to the door handle. And when that attraction, that desire to get to the door handle becomes great enough, they will eventually have the energy to actually physically jump through the air. And we'll see that when I now bring the finger close enough to the door handle. Once they have enough desire, boom, we see that they actually physically jump through the air to get to the conductor, and that jumping of electrons through the air is what we call electrical discharge, or what you would just commonly call a spark or a shock. So when you get shocked, that is actually electricity jumping from your finger to another object. This works well only with conductors because being a conductor, it has to be able to take away those electrons really quickly. If that door handle was made of plastic, for example, there wouldn't be any static discharge because the plastic, being a good insulator, doesn't have the ability to take those electrons away. So the size or the power, whatever you want to call it, of the spark is determined by two things. And that's basically how much of a charge have you built up and what distance does it have to jump through the air. So again, if I keep his finger far away from the door handle, I can rub his finger quite a bit with no spark taking place. But as soon as I get that finger just a little bit closer, as soon as that desire to get to the conductor is big enough, it will make the jump. And you'll notice that the closer your finger is to the door handle, the less charge is needed to actually cause the electrical discharge to take place. Okay? Whereas far away, we can get the discharge to take place, but it needs to have a lot of charge build up. And that'll be an interesting intro to lightning, because lightning is actually the exact same process. That one's going to hurt quite a bit. Lightning is actually the exact same process, just on a much more massive scale. So there's a couple videos for you to watch on lightning, and then there's this diagram and description of the textbook. But the idea is the same. Basically, due to the turbulent nature of a thunderstorm, which is why it doesn't happen during just normal rainy days, the cloud becomes greatly polarized. So the bottom of the cloud develops a massive negative charge. The top of the cloud develops a positive charge. That's due to the updrafts and the downdrafts, all the various turbulence in the cloud causing ice particles and liquid particles to bounce against each other. And as we know with induction, that massive negative charge within the cloud repels other negative charges in the ground. So you can see that the surface of the ground and any tall objects end up with an overall negative charge. So just like the simulation, now there's a massive amount of attraction between the electrons in the cloud and the positive ground. Now, they can't easily get through the air between because air is a very good insulator. But if this charge buildup becomes big enough, just like we saw in the simulation, eventually that desire, that energy to actually jump through the air becomes big enough. And it actually happens. So what happens is you start in it with a small trail of charge passing through the air. This is the more complicated step. You'll see in the videos that they call it a stepped leader. But eventually, once that invisible pathway of charge connects cloud to ground, it's like you've suddenly just connected an electrical wire. And so there's a massive sudden discharge of all the charge from the cloud to the ground, a huge amount of energy and heat, and that's what we see as the lightning bolt. That lightning bolt is no different than the spark you get when you touch a light switch or a door handle. It's just happening on a much bigger scale. And that heat is so intense, it's actually hotter than the surface of the sun. It causes the air around it to greatly expand really fast, and then it comes crashing in on itself. And that's actually what creates thunder. So thunder is actually air molecules colliding with each other. So thunder and lightning are actually the same thing happening at the same time. It's just we always see lightning before we hear thunder due to the different speeds. So that's the lesson on electrical discharge. Go through it, pay attention carefully to it, and then starting next week, we'll be able to move into current electricity.